Morning, everybody. Thanks for joining me here. Today the last day on the floor at DAC, Wednesday, so happy Wednesday hump day to everybody. As Sean said, I'm going to talk about world's fastest DDR this morning. Just a quick word on Uniquify. We are here on the floor. We're over at booth 1013. That's not too far over that way. And I can only skim the surface here today, but you can come to our booth. We've got our world's fastest DDR4 running in the booth. We also have what we believe is the fastest DDR3 running in a wire bond package that we also have running in the booth. Uniquify is actually started, and it still is, a major chip design company. So for a lot of the world's largest systems companies, we do their ASIC and SoC designs, and about 5 years ago, that led us to realize that DDR was going to be needed in the majority of these chips, and that with the increasing speeds of DDR, there needed to be a different approach to it. So that's what I'm going to share with you today. Like I said, just scratching the surface. So about 2 weeks ago, we announced that we had achieved 2,800 megabits per second in DDR4. This is at a 28 nanometer process, and this is using parts from our one of our partners, memory supplier SK Hynix, that are rated for 2,400 megabits per second. So in a sense, I guess you could say, if you were a gamer, you'd say we're overclocking them. But essentially what we're doing is we have built into our system circuitry in the PHY that allows us to very tightly control the timing window and the capture point on the fly. That's what I'll talk about today. So we make this claim, we have the best performing DDR out there. But that's not all, and because of this special patented technology that we've embedded in the PHY, we've been able to get rid of a lot of the normal circuitry that you would find in a DDR PHY that's used for synchronization and so forth. So we also get the smallest area, the lowest power, the lowest latency, the fastest bring up, and when it's running in the field, the best system reliability, and also actually better part yield, because this circuitry we have runs a little algorithm, and if a part can be made to work, a system, meaning your ASIC and the package and the board and the DDR, we'll find a solution that works. So now, many of you are probably sitting there going, yeah, right. No way. How could you say you've got the best performance, but you're going to give me lower power? That makes no sense. Well, yeah, and like our guy there that's getting a raise, it says, oh, it's got to be too good to be true. Well, it actually is true. And like I said, I will encourage you to come visit us later, but I'll try to share some of the secrets with you here. So if you think about DDR historically, the way that designers go about, you get your chip back, you put your test chip, let's say, in a board. What do you do first? Well, you want to make sure the chip's alive. So you apply voltage and get the clock running, and okay, is it smoking, or does it actually look like it's running? Good, it's running. Now, if it's an SoC, usually the next task is let's get that DDR interface up and running. Why? Because I've got a processor and I need to get my software going. I want to start running some code and see what happens. Well, to get that DDR interface running, the typical way that it is approached is you go to the bench and you start trying different delay settings, if you will, usually programming registers to try to get the DDR clock and your system clock lined up. Now, I realize I'm simplifying it, but basically you're dealing with a clock that's coming from your DDR RAM, your external SD RAM, and somehow you've got to capture that data with the clock it's supplying and ultimately get it into your system. And it's kind of like banging around in a maze. I have talked to designers that have told me it's taken them, a week, 2 weeks. One guy said almost a month to get the DDR up and running where they could actually start running code on it. So I call this modeling. They're trying to model the behavior of the system by trial and error, taking lots of parts, finding out what works and what doesn't. We fundamentally take a different approach, and this is based on this technology we have that's patented now in our PHY. We measure it. No two systems are alike. No two chips are alike. No two packages are alike. No two SDRAM parts are alike. Every one has a little bit of variance, and then when you throw in the variations that go on when your system's running, in terms of temperature, voltage over time, so forth, things are moving around. And at DDR1, we probably didn't care. But at DDR4, we're looking at timing margins that are under 300 picoseconds across the whole system. So if you have variance in the package, the board, your external RAM, or your ASIC that adds up to more than that, you got a big problem. So we measure it. When I say DDR subsystem, what I'm referring to here is basically the piece that you would see on your ASIC or your SoC. That's the interface between your processor or whatever else you have running and the external RAM. So there's a DDR controller, there's the PHY, and then there's the I/O, the high performance I/O. We supply all of these. It's part of our business as an IP supplier. The technology I'm going to refer to is actually built into our PHY. There's two pieces: dynamic self-calibrating logic, which operates at the byte lane level, and then there's dynamic adaptive bit calibration that operates on the bits within the byte lane. So let's take a hypothetical example here, where at the pretend that I didn't hit that button. Let's see here. Wow, hit the wrong one. Here we go. So imagine that after a lot of time on the bench, you determine that over a wide range of parts, your timing window, the fastest and the slowest, were about this far apart. And so this orange line just represents the capture point that you programmed into the interface, saying, okay, this is where I'm going to look for the data. And that's all well and good, but the reality is, and our partners and including us working in the lab, over time, timing changes. Temperature goes up, temperature goes down, maybe leakage goes up, and that causes a little sag in voltage. The point is, if this is a fixed capture point, at some point, you're liable to run into trouble. And here, the timing window now is, there's been an excursion, and we're right at the edge, maybe even outside it. Okay, I admit it's dramatized, but I could tell you we have a very large manufacturer of HD TVs that actually dropped the solution they were using and now have standardized on our PHY for this very reason. They were getting a lot of sets were getting returned from the field, sets that were customers put into cabinets, they got too hot, and the DDR system was failing. Okay, so this is the modeling approach. This was our model. This looked like the best point. This is our approach. Same picture. The green line is our capture point, and DSCL is actually running during system operation. No impact on the memory bandwidth, and it's actually moving that capture point along with the window. And in fact, there's one other very cool benefit that comes out of this, and this is why we can run DDR4 at 2800 megabits. The typical, if you're not using this, in the past, what customers, including our HD TV customer that I mentioned, what did they do? Well, as a fix, they just slowed the clock down. Because if you slow the clock down, the net effect is you move these two blue lines apart. They're wider. And now you can do that far enough, you're not going to have any failures. But what does that mean? Well, that also means that your performance, you've given up some performance. We can do just the opposite. And in the case of the DDR4, what we did is we actually sped up the clock. We're pushing those blue lines closer together. But because we know that we're always going to stay right in the middle, we get a very clean sample. So that's the net effect of the DSCL. And like I said at our booth, we'd be happy to tell you a lot more about it. That's at the byte lane. Now think about the bits within a byte lane. They're all coming, flying at your interface with one clock, the strobe, DQS. And what happens? Well, it's pretty typical that unless you have a completely perfect world, there's going to be some bit-to-bit skew, no matter how careful you design your product. And in particular, I mentioned our DDR3 running in a wire bond package. If you've got wire bonds, you've got all kinds of signal integrity issues. You've got little inductors, that are connecting the pads out to the package and so forth. So this other technology, again, runs automatically. It's in the PHY. It's called dynamic adaptive bit calibration. And what it does simply is it takes and aligns all the bits to create a very clean and stable eye for sampling. And that's also embedded in the PHY. So I mentioned less area, lower power, because it sounds like, well, if you can do all this, I can't believe that you're not, giving me a bigger PHY. It turns out that what we do as an IP provider, we actually customize the PHY to exactly match your pad frame. And the pad frame could be along an edge of a chip, two edges of the chip. It could wrap around the corner. We have a very flexible PHY layout. It tends to be very long and narrow. And here's the important thing. Unlike the other PHYs out there that tend to be square, and that means you're going to have to add buffers. You're going to have to do skew balancing. Buffers consume power. They also take up routing resource and area. We butt right up against the IOs, no buffers. So we save a tremendous amount of area. We also don't have that power and overhead in the routing channels. And for the guy that's bringing up that ASIC, I'm going to tell you very quickly a story. I just got it last night from one of our customers. But because of this dynamic self-calibrating logic, we actually you basically run a routine. You do a few register writes when you're bringing that chip up, and SCL runs this routine, which is basically a discovery routine, to find out what parameters are going to work. It initiates the DDR system and comes back and either gives you a pass-fail. If it fails, it typically means, and this is what we've seen most often, there's a problem on your board, like there's a problem with a trace. We've also had a customer that called us to say it failed and then called us back to say they forgot to put the DRAM on the board, and no wonder it didn't work. This bring up, though, as I mentioned, can typically take days. Yesterday, our customer overseas, this is actually in Korea, got a chip back out of fab and into the lab at 2:30 in the morning, local time. Our two guys that are over there, we always like to be involved in bring up, came over. By 3 o'clock, they'd verified that the chip was alive. And by 4:30, using these routines, there are 3 DDR interfaces on this chip. All 3 were up and running at 933 megahertz, which was the target speed. So we're talking, it wasn't even 5 a.m., and basically all DDR was up. They were able to start loading software into this chip. Consumer product, so this is why everybody's working all night. Very tight margin on getting it to market. So to summarize here, and this is why, again, I encourage you to come to our booth, not only the highest performance, but there's all these other side benefits, particularly this one at the bottom. If you're very interested in your product being long-term successful, has to go into a lot of different environments, very important. So I would encourage you to come see us over at booth 1013. As I mentioned, we actually have real chips. They're both in 28 nanometer technology running. We'd love to talk to you more about it. And if anybody has any questions, I'd be happy to ask them. But I thank you for your time this morning, and have a good DAC. Hope to see you later.